So we are looking at the bias theorem. So under the bias theorem, I'm simply saying that the bias theorem just helps us reverse the conditional probability, the conditional probability rules, where we are being taught to say find the probability of B given A when we know probability of A given B. Just the reverse. You want to find B given A given that you know A since you know A given B. So the reverse, just reversing the conditional probability. So now, what do we know? Number one, we know that probability of A given B is just basically equal to probability of A intersection B over probability of what? Of B. That's what we know. So we know that case. So what am I going to do? We want to find the probability of B given A. B given A, according to the conditional formula, is still the same concept, probability of A intersection B over probability of what? Of A. A given B, A intersection B over B. B given A intersection B over A. Now, we want to manipulate this formula so that we can be using A given B in this. So what do? From this concept here, we are going to make our intersection the subject. So making this guy the subject, this is just the same as saying probability of A intersection B is just basically the same as saying probability of A given B multiplied by probability of what? Of B. So this guy is going to be replaced in this, so that we can have probability of B given A to be equal to A intersection B will be given by this guy now. To say probability of A given B multiplied by probability of B over what? Probability of A. This formula is the one which we are calling to be the bias theorem. So every time we're talking about the bias theorem, we are using this formula, meaning that probability of B given A is equal to probability of A given B multiplied by probability of B over probability of A. The same is happening if you want to find the probability of A given B using the bias theorem. It means the probability of B given A multiplied by probability of A over probability of B. This is the bias theorem formula. Yeah, okay? Now let's look at just an example under the bias theorem. Now, I want us to use the previous example which we did under the total probability event, where we talked about defective machine, either coming from machine 1 and machine 2. Remember the question which was saying, suppose that a factory produces 60% of its product from machine 1 and 40% from machine 2. The probability of a defective item from machine 1 is 5% and from machine 2 is 8%. What is the probability of that non-can, which we did previously? Now, using the same question, I want us to look at what is the probability that it came from machine 1. If a product is found defective, what is the probability that that product came from machine 1? What is the probability that that product came from what? Machine 1. So, we're talking about the probability. So, we're talking about the probability of looking for machine 1 given that it is defective. The probability of an item coming from machine 1 given that that item is what? Defective. But if you look at the data which we had in the previous example, we have just defective given that it is M1 or M2. So this formula using the bias theorem, what does it say? M1 given D, this means I'm talking about probability of D given M1 multiplied by probability of M1 over probability of what? D. That's according to the bias theorem. So we just replace what we have. So we already have this in our question. In our question we had this guy, the percentage of an item to be defective given that it is coming from machine 1, which was about 5%. So it means that in this case the probability is 0.05 multiplied by machine 1 was 60%, which is 0.6 over defective item was is it 40%? Defective item was 8%, yeah. So defective item was 8%, which is 0.062. So from the previous question. So probability that it is defective given that it is coming from machine 1 multiplied by probability of machine 1 over probability that it is defective over the probability that it is defective. Sorry, probability of that it is defective, we found it from the previous example, which is the total probability. So from the previous example, under the total probability rule, the previous video, we talked about the total probability rule, where we simply talked about the probability of D, we found it to be 0.062. This was found from the total probability rule. So it's the one which we are going to replace at this position. So this was found by the total probability rule in the previous example. And then now we want to find that the item it is from machine 1, given that that item is defective. So this is how we are going to have it using the bias theorem. It is just a reverse. We know this. Now we want to find the reverse M1 given that it is D, but we know that it is D given that it is M1 from the question. So when you handle it everything well, we have a situation whereby everything will be 0.4684 as the probability for a machine is coming when a product coming from machine 1, given that it is defective. So this is what the bias theory simply explains in most cases. Yeah, thank you very much. So I'll be able to post through the task or the exercise of the question, try it out, be able to send in your solutions. So you look at all the rules we've talked about so far, from the additional to the bias theorem. Understand them, go through the videos from video number 1 to this bias theorem and be able to understand them. The next thing we're going to do, we're going to send in the document of practice solution and practice questions under the probability rules, so that you can be able to go through the documents, work them out, and be able to perfect yourselves. Yeah, and then after that, we'll be able to now look at the probability distributions, the random variable. I'm sure I sent a document already in your WhatsApp group under random variables. We talk about probability distributions as well. You can, after this, you can go through that document, look at those questions in the document, and also be able to send in some more videos concerning the topic. Thank you very much and have a blessed day.